discussion about the relativistic merging stars from the astrophysical points, where the first pioneering works preparing in this institute, in Institute of Astronomy, Professor Tutukov and Jungerson and her team of the scenario machine predicted the some frequency of the some merging rate prediction in 1987.
Really?
30 years ago we discussed it in this, but now situation is very good. LIGO-VIRGO project is is going very successfully, and we all scientific community wait of the new discovery from the LIGO-VIRGO community. But scientific community is very interesting the details of the observation, the details of the problem of the interpretation gravitational wave signal. What about you? Maybe about you in your talk. We wait, and you can start here. You have the in computer. Женя, заряди. Вот. Ладно, я пойду туда сейчас. Да, у нас есть вот такая вот.
Thank you.
Which one?
Scout stickiness.
Okay. Well, thank you for having me today. My name is Ryan Lynch. I'm from MIT. I work with the LIGO-VIRGO collaboration. I do LIGO data analysis. So I'm one of the people responsible for actually analyzing the data and coming up with detections. So I'll give you a little overview about that today, but I'll also try to go into the EM follow-up aspect, the electromagnetic follow-up, and what kind of science can be done once we have detections, and share it with astronomers. So I'll start off by highlighting 2016 was a very good year for experimental gravitation. If you extend 2016 a little bit, we'll see that in December 2015, LISA Pathfinder launched. This is kind of a prototype version of LISA. If you don't know what LISA is, it's a space-based gravitational wave observatory. Funding had gotten cut from the American side in the early 2000s, but the European side of things kept it going, and they launched a prototype in space. A few months later, in February, we published our first detection, GW150914. When you see these, it's the first two numbers are the year, the second two are the month, the last two are the date. So this is September 14th. We actually made this discovery, but didn't publish until February. These were two high mass, about 30 solar mass each, black holes that in-spiraled, merged, and created another new 60 solar mass black hole. So this is our first discovery. It was very well received by the scientific community. A few months later, in June, LISA Pathfinder released some preliminary results showing that they were able to complete a measurement of their noise background, which is a very good sign for the space-based mission. If you go a couple days later, it always seems like we're trying to steal LISA's thunder. But we made another announcement of a second detection, also higher mass black hole systems. So this was in June, and then a year later, we made one final announcement of discovery, GW170104. So these first two detections happened in our first observing run. We started our second observing run last November, and in January we made our third detection. So this was in the second observing run, another binary black hole system. So as a result, this is in the past 2 years, this is what we've added to the knowledge of black holes. Before LIGO, we only had this small number of black holes known by X-ray binary studies. And in a couple of years, we added 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 black holes. So these are the 2 progenitor black holes and the final black holes that they merged into. So this is all in the past 2 years. And our detectors aren't even at full sensitivity yet. So we're very excited to add more detections of this, and maybe even binary neutron star systems.
But initial mass less than 30, yes?
Yeah, so the initial, these are the 2 initial.
I see.
So most of these you'll notice were higher mass systems, higher mass than we ever observed.
Because this picture gives some confusion about the different nature.
Yeah.
Directly, but really the difference is not very high.
Yes. So these are the initial masses.
Yeah.
Here, and these are the final masses.
That's a magic mass.
Yeah.
Not a magic, twice.
So what is all this fanfare about? What are we trying to test? So gravity's been around since Newton, but Newton's theory of gravity was rather simple. And it still works well, but only on very, on mass scales that are very light, low mass systems, very distant systems. We've never really tested Einstein's theory of gravitation in such a strong field limit. What Einstein said with general relativity, which you probably all know, being astronomers and physicists, is that you can think of gravity as curvature. And anything with mass or energy curves space-time itself. And what gravity is you're really just following these lines, these geodesics on this curved surface, and that's the force you feel. But again, we've never really been able to test Einstein's gravity in the strong field limit. Most of the tests of his gravity were, gravitational wave lensing, but those are kind of weak effects. So LIGO is really the first probe of the strong field limit. Well, maybe not the first. We had Hulse-Taylor, but that was still relatively weak compared to what we're testing. So what are gravitational waves? Gravitational waves you can think of as an analog to electromagnetic waves. In electromagnetism, your fundamental unit is the charge. Anytime you have a charge accelerating through its fields, it radiates away energy in the form of electromagnetic waves. Gravitational waves are very similar. It's whenever an object with mass accelerates through its space-time field, it radiates away energy in the form of gravitational waves. Gravitational waves are quadrupolar, so they're a little different than the typical EM dipolar waves. They have this kind of weird polarization signature where simultaneous one axis is getting squeezed together while the other is elongated, and then it alternates. So that's the signature they leave in space itself. They actually change the shape of space. They're expected to propagate at the speed of light, and unfortunately it's a very weak effect, which is why it's taken so long for us to discover these things, these events. The displacement at Earth of space itself is on the order of 10 to the minus 18 meters. So our experimentalists have done a great job. This is 1,000th the size of a proton. They've done a great job trying to get to the level where we can actually measure such a small effect. Then my job's very easy once they have the data. I just have to look at it. So briefly go over the gravitational wave spectrum. I don't know if you've seen this before, but we expect gravitational waves to populate all types of wavelengths. LIGO is just at this very high frequency, tens of hertz to thousands of hertz. Basically, the audible frequency is what LIGO is measuring. So this is supernova explosions, spinning pulsars with asymmetries, binary neutron star and binary black hole mergers. So this is really what LIGO is focused on. LISA will be able to move to longer wavelengths, so supermassive black holes at the center of the galaxy. Pulsar timing can do similar wavelengths. So pulsar timing is you have telescopes point at pulsars and you measure the correlated movements in the pulsars. As gravitational waves pass through, you can see correlated movements and wobbling of the pulsars. And then BICEP is an experiment that's trying to measure gravitational waves released by the CMB background. At the time of the Big Bang, there were very long wavelength gravitational waves emitted. So we're focused for LIGO just on this very high frequency part of the spectrum, but in the next couple of decades, we should be seeing gravitational wave measurements across the board, across the entire spectrum. So what kind of science can we do with gravitational waves? Well, I already talked about compact binary mergers. This is binary compact objects who are in a bound system orbiting each other. And as they orbit and accelerate, they release energy, radiate away energy in the form of gravitational waves, and they move closer and closer together until they finally merge and bring down to this stable final black hole product. So this is the predicted waveform. You have this kind of chirp up as it inspirals and emerges, and you get a little bit of stochastic movement, and then it brings down to a stable oscillation. The nice thing about this waveform is we can reproduce it. The first part we can reproduce analytically, and numerically we can actually solve the whole thing. So we have actual predicted waveforms that we can search, we can sift through our data. So this is, we really have this prediction, and searching for these types of systems is very easy because we know exactly what they're supposed to look like. Another type of kind of predicted source is periodic waves. So these are, you can think of pulsars if they have some kind of mountain or asymmetry on them, or if they're oblate. So any asymmetry that as the pulsar is spinning, if it wobbles a little, that asymmetry will radiate itself away in the form of gravitational waves. So these will be steady monochromatic signals that we can search for in our data. We also have, so both of these types of sources, if a neutron star is involved, we'll be able to study the equation of state of neutron stars, the internal structure of neutron stars. So we're really hoping for a neutron star to show up soon. If we just have black holes, that's fine. We can do a lot of population studies. We can do a lot of tests of GR. So there's a lot of good science that can come from compact binary services. I'll also mention that we have a stochastic background search. So these same gravitational waves that the Big Bang emitted that BICEP is looking for, most of the energy there is at very long wavelengths that we're not sensitive to, but there is a tail that goes down to higher frequencies. So we're hoping maybe to make some cosmological statements. This probably isn't for a few years until we get more sensitive, but there is a tail of basically background gravitational waves that we can make a statement on coming from the Big Bang itself. There's also individual black hole mergers that we can't resolve as transient events. But if you go very distant, you get a lot of very weak mergers. And these add up in our detectors as correlated noise. We're looking for kind of what the black hole background is. So my specialty is none of these three. It's actually gravitational wave bursts. They're often known as unmodeled bursts. So there are some types of sources, supernovas are a great example, core class supernovas, that we expect, because it involves a very massive object and a very energetic event, we expect to release some sort of gravitational radiation. We just don't know the exact waveform. So this is kind of the problem I try to work on, is how do we detect something that we don't know the exact waveform for. So these are some, we have numerical simulations that kind of predict what a supernova waveform will look like. But you can tell it's kind of stochastic. We don't have really a predictive way to predict these, so you can't really use the same template-based models. But you can also think of these searches as kind of a safety net. If we get any weird black hole systems, maybe they're not circular orbits, they're asymmetrical orbits or elliptical orbits. The standard compact binary searches might not pick up on them, so you might need this kind of burst search that doesn't assume any morphology or any template. You might need this to make a detection. So these are really searches for sources that are too poorly understood to be modeled. Hopefully there's something unexpected, some new physics that we haven't seen before. That'd be great. So my specialty is really short duration gravitational wave bursts, where the gravitational wave signature is only a few milliseconds to a few seconds. There's also longer duration events. These might be if two neutron stars merge, and kind of before they'll form a very heavy neutron star that might be unstable. And if it's rotating very rapidly, it might not collapse directly down into a black hole, or it might not collapse to a black hole at all. But as it's rotating very rapidly, this unstable kind of proto-neutron star might develop some kind of bar instability and release gravitational waves through that asymmetry. So this is what I work on. I'll briefly go into discussing this, but today's talk will be more of a focus on, once we make these detections, either gravitational wave bursts or compact binaries, once we make this transient detection, what can we do? What can we share with our astronomers? What can we hope for? So our detectors, it's basically, as I mentioned, that the gravitational wave causes this, this stretching in one direction and squeezing in another direction, this kind of differential motion. Well, the type of experiment that's directly sensitive to this kind of differential motion is a Michelson interferometer. So our detectors at 0th order are just very big Michelson interferometers that you probably saw in your first experimental lab class. So currently we have two interferometers in the United States, the LIGO interferometers. One's up here in Hanford, Washington, the other is down here in Livingston, Louisiana. A gravitational wave traveling at the speed of light. It takes about 10 milliseconds to get from one to the other. That's the baseline separation. We also, as of late July, have a detector in Cascina, Italy. This is a Virgo detector. It's a little bit smaller, so a little bit less sensitive, but it gives us a longer baseline. So we can, as I'll mention in a little bit, we can localize things on the sky a little better because this is separated 25 milliseconds away. There's a 25 millisecond speed of light baseline between the LIGO interferometers and the Virgo interferometers. So this is the current network. We're hoping that by 2020, we add a few more detectors. I'll note that we also have the geo detector. This is one of the initial detectors. It's in Germany. You can see it's only 600 meters long compared to 4 kilometers and 3 kilometers. So it's not very sensitive, but this is still operating. But its data, it might be a little obsolete now. The most likely next detector to join our network is in Japan, the Kavli experiments. This is another 3 kilometer long detector. It's already built. They're currently just commissioning it and trying to get it to where it's stable and can make measurements. So hopefully in the next couple of years, Kavli will be up and running and add to our network. And the Indian government okayed the construction of LIGO India. So we don't know when LIGO India will be constructed, but hopefully in the next 4 or 5 years, we'll have another interferometer in India. So the field of ground-based gravitational wave astronomy is booming. We're having a growing network that will help us make more detections and localize better and estimate parameters, really do better science. So it's really nice to see this all coming together. So these detectors, as I said, measure differential arm motion, and that kind of differential arm motion, you can think of a Michelson interferometer. We have it set up so the dark fringe is on our photodetector. So the light goes down the 2 arms. There's differential arm motion that causes phase differences. As the light recombines, we see this phase shift on our photodetector. So we started on a dark fringe. As we see differential arm motion, this moves off a dark fringe onto a light fringe. So this is the readout we actually see in a time series. So this is our main kind of gravitational wave time series. We generate about 20 gigabytes per day of data just from this main channel itself. We also have a bunch of auxiliary channels, stuff like seismometers, accelerometers, magnetometers, to measure any physical disturbances that are affecting our detectors. So this is in case, say there's an earthquake that happens right between 2 of our detectors, and it kind of looks like a simultaneous event in both our detectors. We can look at our seismometer and say, no, this was an earthquake, we measured it, this data isn't good. So we might see a signal that looks kind of like a gravitational wave, but we'll veto it. So if you're an astronomer and you're getting alerts from us, any alert you've gotten has used these kind of environmental sensors to veto the event. So we produce a lot of data. There's a lot of data we have to analyze, about 2 terabytes per day of data that we have to analyze. So what we're really fundamentally limited by in our detectors is the noise background. As I said, we have to make displacement measurements that are about 10 to the negative 18 meters. And really the way we do this is we push noise in this kind of central 10 hertz to 1,000 hertz in this band. We push this to either low frequencies or high frequencies. So we have a very steep cutoff at low frequencies, where we have a lot of noise. And basically, the lower this curve is, the better we can detect sources there. The further away we can detect sources. So you'll notice that this, as I said earlier, this frequency range is actually the audible frequency range, which is nice because if we detect events, we can actually play them through a speaker and listen to what they sound like, the actual frequency, time frequency signature. So that's why you'll often hear people refer to gravitational wave astronomy as kind of observing the universe with our ears instead of our eyes. It's not quite that, but you can actually hear the signals, which is nice. But this is basically our fundamental cutoff. So this is why we can only detect kind of small solar mass black holes, or maybe intermediate mass black holes, because the supermassive black holes, their frequencies are way down past there. So this is kind of our sensitive region. So really, the way we are able to detect signals is because this noise that I just showed, and the time series of this noise is an ergodic time-dependent Gaussian process. What this really says is that in frequency space, the bins are independent and Gaussian distributed. This is nice because we model our data as some noise time series, some background noise. We say this is Gaussian, plus some gravitational wave signal superimposed on top of it. So if you take the difference, d minus h, as you see down here, you're left with just noise, which is a Gaussian distributed variable. So we can write down a very nice compact form of our likelihood. It's just Gaussian. It's just a Gaussian distribution. So what we're really doing when we're looking for our signals is just trying out different templates for our signals, h of t, and plugging them in this formula and calculating the likelihood, and we kind of find a maximum likelihood approach, or you can take a more Bayesian approach and find posteriors. But this is all our signal detection really comes down to. It's zeroth order. And it's all because this noise is a Gaussian process. So as I mentioned, it's very easy to detect signals if we know h of t. We just try a bunch of different h of t's, see which gives us the maximum likelihood. We can calculate p-values to see if they're consistent with just Gaussian noise, or if we can disprove the Gaussian noise alone hypothesis. What happens if we don't know the signal? So what about these sources like supernova, where we have a general idea what they look like, but nothing to really predict h of t, nothing to really predict the signature in detectors? So really we have to go to the first principles and carefully apply the few constraints we know. The first constraint we know is that these gravitational waves move at the speed of light. So there's some time window that these events must show up in each of our detectors. I kind of have, it might be hard to see, but this diagram here shows a wave front moving over time through space on a given trajectory. So this is the k vector coming down to the left. You see this wave front moving through at the speed of light. It'll hit our first IFO at a given time, and then there's a certain time window at which it must pass through the second IFO. And this tends to be 10 to 15 milliseconds for the Hanford-Livingston LIGO detectors, about 25 milliseconds for the LIGO and VIRGO detectors. And that basically comes from if it's moving edge on. But there's this maximum time window, and it's pretty short. It's only on the order of 10 milliseconds. So even though our noise background might have non-Gaussian artifacts, maybe an earthquake happens and causes a spike in our detector, and we see these kind of transient events in our detectors, these transient noise events that might look like signals, and they happen at a given rate. The chances that they happen within this small time window is very rare. But it's not impossible. It does happen. Probably like once a day we see these. So then how do we say, well, why don't we make one detection claim a day? Because the other thing we know from general relativity is that these gravitational waves don't interact very strongly with matter, so their signal shape is basically unchanged as it passes through the detectors. So the same exact signal that passes through IFO has to show up in IFO2. It has to have the same kind of waveform. And this is modulo projection effects, versus how the detectors are oriented. So we basically know that to make a detection, we need to see two signals that look alike show up in a very narrow time window between our two detectors. So that's the basic idea. Once we have these kind of two constraints in place, we can do two things. The first thing we can do is use the two detectors as templates against each other and say this is our data in one detector and the signal has to be in there. We can kind of correlate that against our second detector and kind of do some kind of template filtering like that. But there's a lot of noise involved, so that's noisy. There's another approach, which is the approach I take, which is you try to break down the signals into its principal components. You take some kind of linear vectors or linear function space and try to reconstruct your signal this way with different basis functions. So as an example, this is our first detection, GW150914 up here. You can see it's the waveform has a lot of structure to it, but it doesn't look like any single simple function. It chirps up in frequency over time, the amplitude increases, the frequency decreases, and then it brings down there. Well, what if we try to decompose this with a Sine-Gaussian basis? So by Sine-Gaussian, I mean it's a Gaussian packet in amplitude. It's a Gaussian amplitude packet with sinusoidal variations with it. So this is an example of a Sine-Gaussian here. So it kind of oscillates with the Gaussian envelope. And this is time on the x-axis, and on the y-axis is frequency. You can see what the Sine-Gaussian looks like when you decompose it with a short Fourier transform. It's got this kind of elongated rectangle shape. You can see if you do the same thing with GW150914, you pick up a lot of the SNR, you pick up a lot of the signal. You can even look in time series, you pick up kind of the highest, the most energetic part. So this is really how we try to detect these unmodeled gravitational waves, is we try to fit Sine-Gaussians to them. And you can think, if you remember Fourier analysis, the more components you have, the better you can do in your reconstruction. So we do more than just one single Sine-Gaussian. We can add multiple Sine-Gaussians, and that's actually, it's hard to see because it does so well. It's very light gray kind of bars around the true signal, red, which comes from numerical relativity. You can see it matches well. That's just adding in more wavelets until you, adding in more wavelets that fit both of the data streams simultaneously. So it can do very well. The code I work on uses just one Sine-Gaussian, and there is a reason for that. So this is my piece of code. OLIB, the name just comes from functions that are used within the algorithm. It's not necessary for understanding, but it's really a search for generic gravitational waves. It uses a single Sine-Gaussian to kind of reconstruct the principal component of the gravitational wave and capture the most energetic component. And the reason we only use one is because this allows us to run at very low latency. It's a full Bayesian calculation that marginalizes all overall Sine-Gaussians. And this marginalization takes a while. So using one Sine-Gaussian, we can do this whole kind of search and make a detection in 10 minutes, which I'll show you in a second is kind of necessary for us to alert astronomers to try to do follow-up science. If you try to do the algorithm that reconstructs this whole complex signal, you might gain a factor of 2 in SNR, but it takes an order of a day to do. So it's a much longer calculation. And this is another example of a Sine-Gaussian. So you have a Gaussian wave with a sinusoidal oscillation. So you might think, okay, this is nice. It might work for sources that we don't understand. But what's the use if we're mainly seeing binary black holes and we know the form of them? Well, actually, 2 algorithms that kind of take this unmodeled approach were the first 2 algorithms to find GW150914. The detection happened when we were in an engineering run, so the data wasn't being analyzed by all the pipelines. The dedicated black hole search algorithms weren't running, and only my algorithm, one other algorithm were running to kind of test out our online running procedure and make sure everything was running properly. So these were the 2 pipelines that found GW150914 and alerted the rest of LIGO. And if they weren't running, we probably would have missed because we would have never analyzed that data. So this kind of safety net approach, it does justify having these 2 pieces of code because we were the first ones to make the first gravitational wave detection. And this kind of shows our detection statement. This is our measured background curve here. This is a significant statement. Basically, the larger this value is, the more signal-like we think it is. And this is the cumulative rate, how often we see events greater than or equal to that. And you can see the rate is orders and orders of magnitude lower that we observe in our background than what we actually observe in our on-source analysis, which at this point, that occurs on a much higher rate than our background is GW150914. So what this really maps in is a 4.6 sigma detection statement. So a very strong detection statement. The actual template searches were able to make much stronger. I think they put a limit at 5 sigma, but it's probably more like a 7 or 8 sigma detection. But the point is that doing this kind of unmodeled procedure can actually work and make detection statements. So that's what I do for my research. I'll kind of stop there and get into something that's probably more interesting to you guys. So what do we do once we make a detection? As I said, my pipeline can make a detection statement in 10 minutes. The other pipelines are on the same order of 5 minutes to 10 minutes, we make a detection. We actually send out this detection statement to our astronomers. We have like 80 astronomer partners. We send out information about the detection for them to follow up and point the telescopes at. So this is what we sent out for GW150914. It's a map on the sky of where we think the source came from. So right now we only have 2 detectors, and if you, well, our sky localization patterns kind of take the form of this ring shape, and there's a very easy reason to understand why. If you remember this kind of diagram I showed with a wavefront coming in, and there's a certain time separation between the two. Assuming a flat wavefront, you can actually see that the timing information gives you an angle from which this wavefront must be coming out of the sky. So this is, you get a ring on the sky. This is why we get kind of these ring shapes in our sky maps. So what our sky maps actually are is this ring shape weighted by where we think our detectors are sensitive, because they're more sensitive overhead than from the sides. So these are what the localizations we get to look like. You can see they're very large. At 90% probability, it's about 500 to 600 square degrees. This is where we have two detectors, so we can only make these ring-like detections. If you had a third detector, you get not only do the two LIGO detectors give you a ring, but you get another two rings, one between LIGO and Virgo, and Hanford, LIGO, and Virgo in Livingston. And these rings will intersect and give you a little island instead. So the more detectors you add, the more you're able to triangulate the source down to a certain point in the sky. So if you added Virgo to this event, we'd probably get order tens of square degrees for localization, which is much more doable. But this is what we send out to astronomers. And we send this out no matter what source we think we detected. We send out the sky location, distance information, and if we expect the source to be EM bright. So if we expect it to include neutron stars with matter involved, it might let out electromagnetic radiation, or EM dim, which are black holes. There's no matter involved. We don't really expect anything. But even for a GW150914, which is an EM dim source, about 20 different of our partners actually followed up on the sky. So people are involved in doing this. So it's
right. I'm sorry because this picture is very often shown here last 2 years, because 90% of this error field observed by Russian telescope master in South Africa.
Yeah, no, Master is one of our MOU partners.
Don't remember.
They're located here, right?
Yes.
Yeah.
I invite you to our laboratory after the seminar to show you.
Oh yeah,
our system.
Definitely, yeah. No, yeah, we have a bunch of great collaborators, and as I'll get to in a second, there's a lot of great.
This is the south.
Southern hemisphere.
Very south.
Yeah.
For the Hawaii and America is not very good.
Yeah,
North
can't pick up.
is not very good, but we do.
Yeah, great. That's we're gonna hopefully in the future we'll have a lot more events and neutron star events that we can follow up on. So why are we trying to do these follow-up observations? This is kind of, I guess, one of the golden accomplishments we could hope to achieve is figuring out what a kilonova is. But I'll get to in a slide. I'll list some of the different science things we can do. It's thought that when two binary neutron stars collide, because there's so much dense matter involved, there's a lot of matter ejected that's radioactive and decaying. There's a lot of EM light being produced. So this happens. So here's kind of a diagram by LIGO-VIRGO on what you can picture the kilonova look like. Here's kind of a timeline on what's being emitted after the detection and how long it takes us to get the information. You can see at about 0 seconds, you get beamed gamma ray bursts. So often you have short duration gamma ray bursts beamed kind of along the direction of angular momentum of the two binary neutron stars. You also have ejecta that's glowing in X-ray and optical. Then you get this kind of broadband kilonova signature, and then you have a shock with the surrounding ISM that gives you a radio afterglow. So you can see the gamma ray bursts happen basically at the time of the merger, it's thought. Then you get into minutes later, maybe minutes to hours, you get this X-ray afterglow. Kilonovas on the time scale to maybe a few days, and then radio afterglow is a few weeks. You see our detection statement comes in a few minutes. That gives us this preliminary localization of the sky. If we get more time to look closer at the data, we might be able to do better parameter estimation. But the quicker we can make our detection and share information with the astronomers, the more of these kind of EM bands can be observed and found a coincidence. So what happens, what can we do if we do find a source coincidentally detected by gravitational waves and by EM astronomers? Well, you can think of it as almost like a Rosetta Stone, because there's these two very orthogonal forms of astronomy that come together at the same event and tell you different things. So one thing you can do is you can get an independent method for measuring the Hubble constant. This is because through the amplitude of the gravitational wave, we can get a distance estimate. And astronomers, if they're able to associate the event with a galaxy, they get a redshift estimate of the local Hubble flow. And through that, you can get your own independent method of H0. So I don't know if you guys follow, but currently the Planck and supernova methods for measuring Hubble's constant are beginning to grow in tension. So this is kind of a third orthogonal way that will hopefully relieve some of that tension. We can also answer the question before, this kilonova signature that we don't really know what causes kilonova, we don't know what it looks like. It's thought that it's caused by binary neutron star coalescences. If we actually observe these in coincidence, we can say here's the kilonova signature that's predicted, and it's coincident with a binary neutron star signature in gravitational waves, so we can pin down if that's actually what the phenomena is called kilonova. We can do the same thing with gamma ray bursts. So there's two different forms of gamma ray bursts: short duration, which is thought to be caused by binary neutron star coalescences. There's also long duration, which are thought to be caused by core collapse supernova. This first one, binary neutron stars, we definitely hope we can detect with gravitational waves. And in the future, we might be able to detect supernova too. And making these measurements in coincidence would really be the smoking gun way to pin down that, yes, these are what causes gamma ray bursts, because we still don't completely understand what's causing gamma ray bursts. So this would be strong evidence to explain what gamma ray bursts are. We can do the same thing with cosmic neutrinos. We have facilities like IceCube down in Antarctica that are measuring high energy cosmic neutrinos. And we can do the same thing. If we measure neutrinos coincident with a binary neutron star merger, we can say this is one of the sources of these high energy neutrinos. And it's not just doing coincidence saying, okay, these things happen together, it must be the cause. There's a lot that EM can help us and help inform us, because if they make this galaxy association of where this event happens and give us a distance estimate, our distance estimates from gravitational waves are kind of rough, because there's a strong degeneracy between the inclination of the source. So as I said, as the sources are orbiting this vector of angular momentum, the gravitational wave source is much stronger if the angular momentum is pointing directly at us, as much weaker if it's perpendicular to us and kind of edge on. So there's this degeneracy here. We can change our distance estimates just by changing the inclination. So our distance estimates are pretty broad. So if astronomers are able to give us a galaxy association so we can pin down the distance, we can do much better in our kind of test of GR, measuring if the speed of gravitational waves is the speed of light, if there is any lens invariance being violated. Measuring, if we get distance pinned down, we can pin down the inclination, and then we can do studies on the beaming angles of gamma ray bursts. So there's a lot of science we can do, probably even more than I could come up when I was making this slide, but there really is. It's a really rich field, and there's a lot of science that should be able to be completed once we start seeing these in coincidence. A couple more slides just to finish up. So that's kind of the really exciting big picture. When we do detect stuff, what can we do? So far, I work on a search for kind of supernova, and we haven't observed any of these gravitational wave events yet. So what can we do even though we don't see anything? We can still put interesting limits. So for supernova, for example, if we know that a supernova occurred, that we observed with telescopes in the nearby galaxy, and we don't see any gravitational wave emission, we can put limits on the energy that must be emitted through gravitational waves. So that's kind of, it's a very uncertain theory how much energy is actually emitted through gravitational waves when the supernova explodes. All the rest of the supernova budget is very well understood, but the gravitational wave aspect isn't very understood. We don't understand that coupling. So the fact that we don't see any kind of unmodeled supernova bursts in our data gives us this kind of curve on what limits we can place on energy, and that we can give to the supernova physicists to kind of help inform their models. We can also just put a rate density on things we don't understand. So basically, everything that's not a binary black hole source, we can put an upper limit on how often these things can occur in our local universe. So we take all detector black holes out and say, how long do we observe for? How far could we see? And there's nothing there. So it's just a simple Poisson measurement to put upper limits on the rate density of kind of gravitational wave transients in the local universe. So our second observing run, we're actually able to improve these upper limits by an order of magnitude. So you can see our paper if there's more interest in that. So there is a lot of interesting stuff we can do offline. It's probably just not as exciting as online.
What is here of this references last year?
This is the paper where we describe this upper limit. It's the unmodeled gravitational wave search.
Yes, because we a lot of time ago discussed the possible dependence between rate, events rate on detector and amplitude of the signals.
Mm-hmm.
No spiraling without information about distance.
Yeah.
And we predicted 1 divided h cubic. The square root from energy is the h, and dimensional
analysis.
Amplitude.
Yeah. So you're saying
The same.
yeah, exactly. So this is kind of
30 years ago.
Oh, perfect. Yeah, we probably.
I give you this paper.
Oh yeah, we probably cite you in this paper. Because
Well,
yeah.
very simple.
Yeah. Great. So as my final slide to kind of wrap up, I kind of showed you some of the different science we hope to do. And I want to stress that this is happening right now as we speak. The first observing run happened in 2015, 2016, like I said. The second observing run actually just happened this past year. It started the 30th of November 2016 and ended the 25th of August 2017, so just a few weeks ago. We're analyzing the data now. So most of this was just the 2 LIGO detectors. In late July, we actually added Virgo. And we performed the searches for gravitational waves I talked about in low latency in real time. And we sent out alerts to our astronomers at a false alarm rate of about 1 per month. So these alerts were shared. I think all I can say is on order of 10 were sent out. So we did share events with our astronomers. Nothing's been, other than the January event, nothing's been published. We're still kind of finalizing our results. So in the near future, you should be able to hear if we made any detections online. And we're performing thorough offline searches, so hopefully pick up a few more triggers too. But yeah, in the upcoming months, we should have results from this data, which should be really interesting. And we're upgrading our detectors currently, but in a year, we'll probably start another observing run that's going to be twice as sensitive in the noise background. So twice, it's nice because the distance we can see scales linearly with how much improvement we have in our noise background. So if you can drop your noise background by a factor of 2, you picked up a factor of 8 because it's distance cubed in volume. So we should have 8 times the number of sources if we can actually hit that factor 2 improvement. So there's a lot of exciting science that we hope to come out of this in the near future. So stay tuned.
Thank you very much. People come. Okay, is there any question? My question's about the very well detected the 2 black hole merging. What do you think about the accuracy of the determination spin care parameter before merging, and some problem with the angle heat?
So spins are very hard to model. One, because it's the way spins enter into our waveforms is kind of a higher order effect. That's very weak. And you really need spins to be very unaligned and orthogonal to each other. Because if they're unaligned and orthogonal, they actually cause precession. So this disk, as the compact objects are orbiting, will actually wobble. And if you see this wobbling, you can kind of progress out more information about the spins. Currently, I wouldn't say we have much evidence for spin aligned versus spin unaligned in our measurements. The reason this is so interesting is it can kind of tell you where these black hole populations were created. If the black hole binary is formed in the field, and kind of just since birth, you usually have this binary, and they kind of both turn from stars into black holes through common envelope evolution. You expect kind of the friction of the common envelope evolution accretion disk to align the spins. So in the field, you expect aligned fins. If they formed in dense clusters, like globular clusters, you expect the binaries to be formed and tightened basically by just black holes running into each other and being dynamically captured. So there, it's a much shorter time scale. You expect the spins to be more isotropic because it's a dynamic capture.
Now, we understand all theoretical interpretation, but my question about the real significance of the detection, because a lot of people now speculated about the spin direction, and in some cases I see the Kerr parameter is equal 0.002 plus minus 4. 20%, 100%.
Yeah. So I wouldn't believe that.
What do you think about the reality of this?
So as far as, the detection, like the detections, I believe that we have very confident detections in the events itself. The parameter estimation for what the spins are, I was an author on some papers that said basically you shouldn't trust any single spin measurements. Anyone that says we have definitely measured the two spins very accuracy, you shouldn't really believe that. There's a few different groups within LIGO that claim the best way to measure spins is on a single event basis, in which you need a very loud events with very high spins that are unaligned, so there's precession. The best way is to wait till we have maybe 10 or 20 events and stack up the different spin measurements to see if there's this kind of distributional alignment versus isotropic distribution. So I wouldn't trust the spin measurements on any single event.
I too.
Good.
Okay.
What final speed?
Final, okay.
Final spin.
Final,
Final spin, yes.
It's reliable.
Because you have you basically have one black hole. It's just a single Kerr black hole that's just ringing down. So there's a much more straightforward dependence.
Very
So
big,
final
0.5.
Final spin you should trust. The progenitor spins, I wouldn't.
About possible merging of neutron stars. I'm not involved in LIGO-VIRGO and don't know any classified information, so I can ask maybe a little bit silly questions. Let's mention that the detection of the merging of neutron stars already was detected or will be detected in the nearest future. It's clear that it will be much weaker than the signal from the merging or from the two merging black holes.
Not signal, initial energy is smaller.
Yes, it will be weaker.
But on detectors the same.
The amplitude will be smaller.
On detectors the same.
Yes, but event will be different.
Yeah.
And my question is, when this event with black holes was detected, what then was done? You take the library of the signals calculated by solving general relativity equations and try to fit one to another and say, okay, this is solar masses, and this black hole is, say, 20 solar masses. What will you do in the case of detection of the merging of two neutron stars? You have to fit with results of very long general relativistic hydrodynamic simulations. And the question is, the signal is very weak. The run or numerical simulations are very long, many time steps. And of course, you have approximation errors. And how to estimate, and after you run, you calculate the form of gravitational signal, also introducing some extra numerical error. And how can is it possible to estimate this final numerical error? Is it correct, and how far it will be correct to fit these signals?
So for neutron stars, the way most of the waveforms are computed is the long in-spiral, the long weak in-spiral part is modeled as a post-Newtonian expansion, because the kind of deviations from GR are less severe when they're far apart. So you first model it as a post-Newtonian circular orbit. You model that, and you can do that all analytically. So the hope would be that matches pretty well. And then when you get closer to the merger, that's when you need the numerical analysis, and you kind of stitch them together and interpolate between the two. But we did similar things with binary black holes to test test our waveforms against general relativity is we took the numerical waveform simulations and the waveforms generated by them for as long as we have. And then we did a match between what we saw in our data, the match between the numerical relativity and the match between our waveforms to see how much overlap. So most of our waveforms are tuned constantly against the latest numerical simulations. But that's really, as you mentioned, only in kind of the merger ring down late in spiral parts.
The most important part and the highest amplitude will be not when you can use post-Newtonian approach, only when you have to use the GR.
So that's the highest amplitude, but it's nice because the neutron stars, the binary neutron star signals last for so long. It's kind of a minute-long signal. Maybe not in our band for a full minute, but at least 30 seconds. And you can actually integrate up this weak signal. And that's where a lot of the SNR comes from. Maybe half, I don't know the exact number off the top of my head, but actually half the SNR and the energy we extract from the data comes from this in-spiral we're using post-Newtonian. Just because it's so long and you can integrate for so long.
Может, краткое резюме сейчас по-русски, может быть. Вы спрашиваете по-русски, значит, речь идет о том, как фитировать вот эти наблюдения, когда у вас не черная дыра, а когда у вас реальные... Ну, да, только коротко, да.
Когда фитируются эти вещи, с чем фитируются наблюдения?
Да.
С численным моделированием, с мержинкой нейтронных звезд?
Нет. Нет. Ну, практически нет. Они берут спиральную стадию, когда у вас они далеко, вам все равно, что там... Не-не-не. Чтобы массы определить, надо знать закон Кеплера, и там не нужны релятивистские особые... Translated самса. Да, но потом наступает очень интересно, и, скорее всего, гравитационно-волновая астрономия даст ответ на вопрос, как устроены нейтронные звезды, потому что предсказать, начиная с массы Оппенгеймера-Волкова, там непонятно, будет черная дыра или нет, есть там кварковые ядра или нет. Это все страшно красивая новая наука, которая будет... We say that the theory of neutron stars, equation of state, Oppenheimer-Volkov limit is very needed. The gravitational wave observation of the last stage of the merging. Yes.
Yes. So that's
but we cannot predict it.
That'll be one of the interesting things we try to measure. So most of our detection will come from the long post-Newtonian in-spiral, and then there's things you have to take into account, such as tides, which depend directly on the equation of state. You don't know how much they're going to deform, when they're going to get ripped apart. So that, I think there's one group in Italy that's been pushing very hard on different simulations, trying to simulate that. But really most of our detection comes from this long, integrating up the in-spiral part. And then we can detect some of the energy. There's a lot of energy there, but our detections aren't solely reliant on the merger part. But that's where a lot of the interesting physics on the equation of state of neutron stars is going to come from, looking at the mismatch between our templates and that. Yeah.
In your talk, you mentioned that you see gravitational waves propagate with the speed of light. It's correct in the framework of general relativity. On the other hand, even in your first publication, you gave some constraint on graviton mass. If we consider some alternative for GR and graviton has really mass, in this case we cannot claim that gravitational waves propagate with the speed of light. And if you're trying to pick up some signal, some information, if you assume from the beginning that gravitational waves propagate with the speed of light, in this case we ignore simply, let us say, these events. Mm-hmm. Could you tell more about the subject?
Yeah, so most of our searches rely on the fact that we assume gravitational waves propagate at the speed of light. Our actual binary black hole, binary neutron star searches are what are known as incoherent searches. So what they're looking for is the gravitational wave signature in a single detector. They just do the full analysis in one detector, and then at the end compare and see what the separation is in distance. And the window we use, it's not the exact. If Hanford and Livingston are separated by 10 milliseconds, we'll actually use 15 milliseconds for the first kind of threshold. But if there's a huge difference between the speed of light, then we would miss signals. But we'd still pick them up on the, so actually the January events, the Hanford detector was not in science mode. So it was first just picked up in the Livingston detector as a single event trigger, that was a loud single event trigger that we looked at and did further studies on. So I think there's possibility. There's also people in LIGO looking for echoes of, so I'm not exactly sure what the theory is, but it's when two black holes merge, there's a light ring that some of the gravitational waves can get stuck in and be emitted later, so you kind of see this echo in your data. We do have searches for that. I might pick up on kind of longer time distances. But it's a good point that it's, if there are gravitational waves that violate the speed of light to a high degree, we are not necessarily optimized to detect those. We do have a couple of safety measures where we might be able to pick up. If we saw something in one detector that looked exactly like a general relativity predicted gravitational wave signal, we would kind of look through backfilter data and see if we could find anything similar. But our automatic pipelines aren't necessarily set up for that. So.
You say about, I have more or less practical questions. So you say about the error field which you distribute to EM collaboration. But for instance, for first event, it was 4 different localization, for instance. And one of that error box have a very simple name with your library. Maybe you can clarify which was the difference between these 4 localizations map, and also which of these is more useful, which we must use as a.
That's a very important because wrote the special soft for the automatical using of the LIGO-VIRGO.
So yeah, just to repeat this question, it's when we send out these maps to astronomers.
Yeah,
this is one.
Not last, maybe, yes.
This is probably the finished product.
Finished.
But we have multiple different estimates of this map. And the first event, because we weren't really in science mode, we weren't fully organized, we sent out multiple different versions. First we sent out this unmodeled, so he's mentioned there's a code with my name on it, or my algorithm's name on it, this library. These were the unmodeled. So you don't assume that it's a binary black hole or a binary neutron star. And you try to do the detection and localization. So it's a much rougher estimate because you're not taking into account the full estimation. As I said, these were the first 2 pipelines to detect the event because we weren't up and running. So I think we sent these out first. Then we ran our analysis that assumes it's a binary black hole or binary neutron star and got better localization and sent those out. And then later we were able to use more complex waveforms and get better estimates. So that first event was more or less our fault because we weren't very organized and we weren't prepared for it. The second observer run, I think we were slightly more prepared. But the procedure is now that we should be following, I think that we have followed, is if we have strong reason to believe that it's a binary neutron star or binary black hole, we only send out that event from the most significant detection. And we'll send first our preliminary estimate, and then we have a follow-up estimate that we were much more confident. We'll send that out later. But yeah, I would always trust, if we send out both an unmodeled and a modeled, always trust the modeled, because we'd only have the modeled estimate if we had some kind of confidence that it was a binary neutron star or black hole. But yeah, that was mainly our fault. It was kind of a bureaucratic. We were kind of a mess, and we were just sending out too much.
I think we just shortly discussed it after the seminar, some questions about the error field maps and so. But now, general astrophysicist, astrophysical questions. Is there any questions more? I have one question because you say that the LIGO-VIRGO project, LIGO, mostly detected the non-spiraling gravitational wave signal during last set. Yes, of course.
In the last.
I mean the non-binary spiraling events.
So we've only made one claim detection, and that was in January. We have,
I remember.
yeah, we have sent out an order of 10 alerts to astronomers.
Yeah.
I really can't say if these were in spiral or not in spiral. So the alerts had a label of which pipeline detected. So if it was sent out by an unmodeled search, that's probably evidence that it might be unmodeled. What I will say is we sent out an order of 10 events over the full year, and we were looking to send out triggers at a false alarm rate of about once per month. So that statement, this is the only reason I'm allowed to say it. It is consistent with all those just being noise, background noise from our detectors. So we haven't made any other claim detection. There are these 10 events that we are currently following up on.
Have you such events before first set of observation? I mean 2 years ago.
2 years ago, did we send out any?
Have you the non-spiraling?
No. So far, the only thing.
Why?
Why? So why do we only detect black holes?
Sensitivity is high.
So there's a few.
What difference?
There's a few different aspects. Our noise curve.
Yeah.
One, we're most sensitive in kind of this 10 to 100 hertz frequency band. This is kind of the merger frequency of these high mass black holes. So this is, as you were saying, the merger frequency has the most and the highest density of energy. This falls right in our most sensitive bands. Black holes are also, we know they emit gravitational waves. We know that they're the strongest emitters of gravitational wave. The heavier the mass, the stronger the energy emitting gravitational waves, which means the further you can see them. So black holes we can see to the furthest. So our horizon for black holes is out to like a gigaparsec. For binary neutron stars, it's closer to 100 megaparsecs, the absolute kind of distance. So we have a much larger volume to switching over.
But my question is more data. You see, the first set very similar to this maybe.
Oh, why?
And we have the smaller sensitivity at the neutron stars frequency. This can be influenced to the result.
Yeah, so the predicted rates were large enough between black holes and neutron stars that we
because
really.
kilohertz sensitivity is very important.
For neutron stars, yeah. The reason we haven't made any neutron stars.
More flat now, maybe, not?
It's a little flatter too, yeah. So we're sensitive to about 2 kilohertz.
Yeah.
And neutron stars, the merger frequency is supposed to be close to 2 kilohertz. So we can capture a lot of the action there, the merger and ring down action. Yeah, my best explanation is we don't really know why we haven't detected any neutron stars yet. I mean, we're still analyzing the data of our second run, so there might be a neutron star in there. Our very first observing run, we didn't see any. And it's probably just because it might be that neutron stars are slightly more rare than black holes. I'll also note that this population of black holes that we detected are all relatively heavy mass that we didn't even know if they existed before. These are, I don't know if they're quite intermediate mass black holes, but for our X-ray studies, we'd only seen black holes up to maybe 20 solar masses. And now we've seen a handful of black holes.
No, this is final black hole.
So the progenitors here too were around 30.
About 30, yes? Not
Yeah, about 30. 30
yes.
35.
It's not, but you must remember that these black holes belong to the low massive binary system, another branch of the evolution of binary stars. These binary stars not produce a gravitational wave at all, because the red stars and black hole cannot to produce large gravitational wave bursts. And this massive binary system, I think this difference between two.
My best answer would be that these are heavier systems, so they emit stronger, so we can detect them out to a further distance. So hopefully once we increase our sensitivity, So the horizon for detecting these is probably 1 gigaparsec to 2 gigaparsec.
Yeah.
The solar mass black holes, these is probably only out to a couple hundred megaparsec.
Yes,
So
this
hopefully-
effect included, of
Yeah.
course. Yes.
So it could be that we're just not sensitive enough, and these are rare enough compared to our sensitivity that we haven't found it yet. So all of our observations were consistent with the predicted rates. The predicted rates did span, I think, 4 orders of magnitude, so they weren't very informative. But really, the only way we can kind of come up with a better explanation is to observe longer. So we just have another year of observation. So hopefully in the next few months, we'll be able to either detect some neutron stars, detect some low mass black holes, or at least have a better explanation, or a better estimate of the rates.
Ну что, тогда поблагодарим товарища. Thank you very much. Very good, very nice, very understandable talk.
Yeah.
And,